Okay, the first day of our distance learning for fourth quarter is actually Unit 10, Day 2. It's because it was split between the blue days and the green days. So this is abbreviated, shortened up a bit. We're going to start with looking at relative dating and absolute dating and what these concepts mean. Here we have a picture of a road cut, probably, or a quarry, and we have a scientist here for scale. And you can see this tan, probably a sandstone on the bottom, which has got a gray layer over it, and then this rubbly looking layer above it, and probably another one on top of it right here. But we can easily make some simple logical descriptions of this. We probably know that this bottom one is the oldest because it's on the bottom, and that this gray layer was deposited on top of it, so it must be a little bit younger. And this rubbly, bouldery layer must be a little bit younger than the gray layer, or somewhat younger than it, because it's on top of it. And then we know that this fault that you see running right through here, follow the cursor, this fault right here is younger than all three of these layers because it breaks all three of them. Okay? And that logic has some fancy names in science, in geoscience, that sound more complicated than they are. These relative geologic age relationships are called original horizontality, superposition of rock layers, and cross-cutting relationships. The original horizontality is the most simple. It's just a statement of what we just looked at. All rock layers are originally deposited horizontally. Now, why does that happen? Well, it's because gravity is going to pull everything down to the ground. And as if you shook up a jar with mud in it or sand in it, the sand would lay out horizontally at the bottom of the jar because of gravity. So that's the same in the oceans too, or in water. So all rocks are horizontal to begin with. Then you have superposition of rock layers. That simply means that the oldest rocks are on the bottom and the youngest are on the top. And cross-cutting relationships describe how that fault cut across those older rocks. So the things that do the cutting are always younger than the things they're cutting. Okay? And you can go back and look at that picture if you'd like to apply those concepts. Here's one way to, another practice for this. Let's take a look at what we have here. You see you have a lot of horizontal beds. You see a fault. And you see some weird squiggle right here, right above that fault. See this kind of rough boundary here. It doesn't have a straight line. So something's happened here. It's chopped off that fault. And then you have two more layers above it. So let's figure out what happened. So the oldest thing, using the principle of superposition, tells us that the oldest rock unit is the bottom one, which is letter L. And then the one that's directly on top of it is Z. And the next one that was deposited on it is A. But we'll notice that there's a thick portion of A here and a not very thick portion of A over here. What happened to this A? Well, first of all, we know that all of them were faulted. L, Z, and A were faulted because this fault breaks all three. But we also can see that the top of A is missing over here compared to over here because which side of this fault was pushed upward? The right side. And when it got pushed up, this was actually the ground surface, and erosion took off the top, sort of like a sander. It took off the top and it left this thinner portion over here. And then some water came back in and this area became submerged again, and a deposit was deposited on top of that, a layer of sediment on top of that, letter Q, and then D. Okay, and this is all just applying those simple concepts. Which ones did we see here? Well, we see original horizontality. The rocks are horizontal. We see that the younger layers are sitting above the older ones on the bottom. That's superposition. And we can see that this fault must be younger than all three of these by cross-cutting relationships because it cut those three. But we know that this fault is older than the erosion because the erosion cuts the fault. And then these rocks are unfaulted, so they must come much after the faulting. Okay? So there's a concept in geology that's really important. Um, it's called unconformities. There are three types, and really the specifics of the three types isn't that important. What's the most important thing is to understand that they represent a break or a gap in the geologic record. There are three types, and you can see the examples at this link. But the uh, the most important thing to be able to do is identify that when an unconformity has occurred, so that you can recognize that some of the geology, some of the history, maybe even some important fossils are erased because of erosion. Okay, so it's a lot like ripping pages out of a book, and if you don't know whether or not 3 pages were torn out of this book or 3 chapters, it's sometimes hard to tell. So it's one of those things we can't avoid it. The earth is always eroding. So we have an example of the angular unconformity here, and you can just see that the folded layers are underneath these flat-lying layers. Here's a diagram that shows you how they form. But once again, what's important to be able to see that erosion took place right here where I'm moving the cursor, because the top of this folded rock got shaved off by erosion, and then later on these red layers were deposited on top. Okay, over here we have a different type of angular unconformity where you can see these diagonal rocks, and they've been eroded off, and then some these younger Triassic rocks are on top of these Carboniferous rocks. Okay, and then the disconformity, and that's the one that's a little hard to see because it's just this squiggle here. This is truly like a stack of pancakes. It could have been, 3 pancakes were laid down, and then 6 more were laid down, and then somebody came by and grabbed 6 pancakes for themselves, and then the cook came out and put some more pancakes down. You won't really know how many pancakes are missing. You might not even think any are missing if you didn't see the person take 6 pancakes. You understand what I'm saying? So the disconformity just tells you that this series is discontinuous. And these are difficult sometimes to spot because everything still remains parallel. And the nonconformity, just you had horizontal beds of sedimentary rock sitting on top of metamorphic and igneous. Geologic history is lost. And this one's a little more challenging, and I'm not going to go through it because I think you guys are getting the idea, and you're going to get some practice in an online activity in a moment. So I'm going to move on. And we're not going to do that one either. Okay, so I do want to talk about this. Lithologic correlation. This is where you connect rocks. Lithology means rock types. And what we're going to do is simply connect the rock types from one location to another. The primary reason for this example is that we're not always lucky to see rocks in cliffs or in canyons or in road cuts. We often have to go digging for them underground using core samples. Core samples are like drilling rigs, and they can drill through the rock to great depth. And they can even be mounted on boats, like in this picture. Now, it's a pretty expensive thing to do, and we don't just do this because we're curious about what kind of rocks are down there. Almost all of this coring is done to look for oil or natural gas. And in the process, this data comes back. So the geologists benefit both in terms of finding oil and natural gas, but also learning something about the geologic history at the same time. So you can see that here's a core sample drilled by the ship, and it drilled another one, and letter B and letter C. And you can see that they have the same layers mostly. This sandstone layer is present in both of these, and all three of these. Same for this, maybe a siltstone, and then this shale, this gray shale. But you'll notice this bluish, light bluish limestone. Whenever you see bricks, that means limestone. That limestone is only present out here in the deeper water. And in the shallow water, where it was into these thinner sediments where things were shallowing up, it's not present, and it actually is a type of unconformity. It's called a pinch out because it pinches out right there. All right. But again, it's just to show you that you can get this lithologic correlation. These might be 10 miles apart. Who knows? They could be very far apart, but a geologist can still recognize the rock types and make the connections by inference. Okay, and index fossils. Index fossils are important because they show us the age of the rocks. These we pick rocks or we pick fossils that are widely abundant around the world, but they only lived in a narrow amount of time, like a stegosaurus or a certain type of a mollusk or something that was living everywhere around the world, but it was only for a short time. And that helps us know the age. If something lived for a very long time, it doesn't help us at all, like cockroaches, been around for a long time. So we're not correlating the rock types here, we're correlating time. Okay, so the rock types may not match anymore, but the fossils will. And so we want to look for the similar fossils in the rocks. That's the key. So here's a good example. You can see that you have this sort of mollusk thing here in this upper layer of looks like a shale, and then in this sandstone there's this like spiral shell-shaped thing, and then in this shale is this other one that looks like an ammonite shell, and then in this limestone you have another one of these clam type looking shells, and then a brachiopod. That's what that is. Okay, so you'll notice here this layer 6 and this other layer 6. Notice that the rock types are different. This is a shale, and this is a limestone, but they have the same fossil in them. So the scientists in this case are not interested in connecting the rock types that are the same. They're connecting time. And the same thing over here. We have another pinch out. We have a pinch out right here. There's a gap because we have this rock layer here and it's not present over here. And then we have this limestone with this clamshell type thing, or snail. And then over here we have it as well, but the rock types are different. So again, once again, this is time, not rocks that are being connected. Okay, that's called an index fossil. It tells you the age of the rocks. I'm going to skip this one, and I'm going to skip all of these, and you'll notice that your notes don't contain these slides. And we're going to stop right here at this break, and now you're going to go to your document, to the assignment document, and there's going to be an embedded video there that tells you how to use the lesson activity. Okay.